We'll now move on to the second speaker of the session. So I'd like to introduce Thomas House from the University of Manchester, who's going to tell us a bit about his work now.
Hello. Oh, hello everyone. So can everyone see the screen okay?
Yeah, we're good. Thank you.
Okay. So this is going to be a bit of talking about stuff that is done and understood, but I guess it's also, as the title I've come up with suggests, a sort of explanation of why certain things aren't done yet. Okay, so I'm going to be talking about why there isn't an ONS official estimate for the generation time, right? But there are lots of other data and hopefully one's coming. So in general, we've been very lucky this epidemic that cases have tended to follow the trajectory of the epidemic. And I think that's led a lot of people to think that cases are the main way or best way to monitor, but ultimately they're biased by factors we don't understand, like testing behavior. So for example, now, the whole, there's lots, those of us who have any engagement with the media are getting lots of media requests to comment on exactly what cases are doing. There was a big problem with using cases as a monitoring data stream. I think it was last September, there was a real problem with capacity. So everyone came back from holiday, wanted to test, there weren't enough tests. It completely, it made the tests a very odd data stream for a bit. I think, as a result of these worries, and for other reasons, we have community studies in the UK, the ONS and REACT study, which don't study from that bias. And this is particularly important if you're also interested in asymptomatic. So because to end up in the test and trace data, you're supposed to have been symptomatic, although when you look at it, that isn't always true. It's missing one of the main reasons that we've all been stuck at home, which is that we can't control the epidemic just through symptomatic issues. ONS is Office for National, yes, sorry. So we use it so much in the UK that, so it's a, it's our national statistics agency. Okay, but the study is a really big collaboration and anyone who wants access to the data can apply, but I'll say why that's not as straightforward as it should be. Okay, so of those two, the ONS is a household study. So why do we care about households? Well, when people get into epidemiology, they normally see the SIR equations, which are of course a special case of what Kermack and McKendrick wrote down 100 years or so ago. But about as old as the SIR equations are attempts to model households, and they're important for various reasons. So you have close repeated contact within the household. Most people live in them, although there are important groups that don't, but of course care homes are homes. So they're really just large households. So most people live in groups. And we design interventions at the household level. So actually this pandemic, we've tended to say stay at home, right? But not try to separate people from their household members, maybe incorrectly, right? This has come up as a question, why wasn't there a policy attempt to allow, there've been recent papers thinking about whether shielding worked as well as we might have hoped, and maybe that things like shielding would have worked a bit better with some thinking about within household transmission as well. But the emphasis remained for policymakers chose for the emphasis to remain on whole household isolation. People with children in primary school in their household are asked to test, for example. So the household plays an important role in what we do, as well as where we live and how we transmit to each other. Just a quick bit of history. So saying it went back, Reed and Frost did the first stochastic epidemic model, and really nice story is they modified a roulette table to do Monte Carlo simulations of it. then Bailey and Hope Simpson kind of took this forward. Theoretically, in Bailey's book, there was a lot of nice development of spectral methods in stochastics, and Hope Simpson did these classic experiments of transmission of childhood diseases in households. Then I kind of split up. I think kind of later in the 20th century, we got Frank Ball's general final size formula, which kind of completed the developments of Bailey. So you can generalize a bit more from what Frank did, and that's very interesting. But I would say that that kind of synthesis meant that we now have the ability to work out some very, very general closed form likelihoods, and then picked up by Adi Longini, Halloran, and others. They would have been mainly looking at, say, the Tecumseh studies. So studies then were based on viral culture. So I think it's important to see the development of theory and the development of empirical work at the same, in the same frame, right? Because science thrives on both being healthy, although this is a kind of mathematical meeting. I think mathematics is influenced much more by empirical science than mathematicians like to admit often. And then this century, we already had a talk yesterday about MCMC, data augmentation in households, and now all the kind of empirical work is done with modern molecular techniques. Now, what I did is I wasn't as advanced as Robin and William, who was talking yesterday, and because of having a big data set and being on a slow computer, I used late 20th century methods, not data augmentation, because they were slow enough, right? So what we're often doing when you're working under kind of extreme pressure to get stuff done is use last era's theory on this era's empirical work. Okay, so here's the preprint, and there are going to be some equations, but the fundamental difficulty with this, compared even to the studies that William was talking about with case ascertainment, is that it's a systematic visit. So it's a household cohort study. So the whole household is followed every week for 4 weeks, and then every month. So here's an example of what you might, so it's roughly a random population study, which is powerful. But in terms of trying to observe household transmission, you can see that if you're visiting someone each week, you don't observe what I've drawn here in red, which is the actual tree of transmission. Yeah, which repeated follow-up studies will often claim to do, like attack or whatever, or recovery. They will have their named index case, even if you don't quite trust that and want to adjust for it, right? In a study based on repeated follow-up, particularly when the gaps get big, we don't even have a starting point really for the transmission route, particularly when you could have someone who comes positive before their infector. That's even a possibility, right? Okay, so what I did was to try and get on top of some things, split the data into 4 tranches. Tranche 5 is just running at the moment, by the way, so we are updating, but these are the ones that have been run and put on archive. So we should have results for Delta appearing soonish, hopefully. But to give an idea of the real size of this study, so the factors we were interested in was household size, the B117 or alpha variant, in this case identified via S gene target failure rather than genomics, age of participant and work in patient-facing roles. And you can see just the sheer numbers that there's over 350,000 participants and 180,000 households, distinct households in total, with just under 20,000 positives, individual positives. So this is kind of data at a scale that I thought we would never ever have for household studies. And while that's brilliant, it creates, like I say, it creates its own problems, because the Tecumseh study was like a few dozen in each box, right? So you could, even though they were running on old 486s or whatever, the numbers were just not as punishing for the computer as this. Okay, so just to define things properly, what's a household? It's a unique partition of the integer individuals in the population. So I've just written this out. So everyone's in a uniquely one household, and the household sort of cover the population. Then I let each individual have a feature vector, if you're using modern things, or a vector of covariates or independent variables, or whatever your preferred thing is. But of course, feature vectors is obviously better if you're trying to jump on the latest hype train, which maybe I am. And each individual also has a y, which is the dependent variable, if the swab is positive or not. And the point is that we have to associate features and swab results with a tranche, right? So what I'm saying is your yi is 1 if you were infectious at some point in that tranche, or if someone else in your household was infectious in that tranche. So we snap households to the tranche in which the first household member became infectious. And then there are other rules for deciding. Some people leave patient-facing work, right? So we decide what's most appropriate for that tranche for the feature vector. Okay, so it's a good idea to do some exploratory analysis. So we do histograms. So the histogram is the counts for the different tranches of this. And the important point is these are really, really, really over dispersed. Okay, you can't see it because the 0 count would just dwarf everything. So I don't show the 0 count. But compared to a binomial or a Poisson or something else, these are extremely over dispersed because transmission generates that over dispersal. So if you have one case, you're more likely than the prevalence percentage to have 2 cases. And for the larger households, you see this U-shaped distribution, so bimodal distribution, which is very indicative of a transmission type process. And the same for the other tranches. So these are very, like I say, these die off very, very much. If they're not bimodal, they die off very much quicker than typical, like maximum entropy distributions, binomial or whatever. And if they and some are even bimodal. Okay. So that tells us there's a signal for transmission at least. Then we can make these density plots, which are kind of 2-dimensional looks at, like it's basically 2-dimensional histogram, but I'm putting things down as translucent squares because you don't have, so that we can borrow power from the different sizes. And so interestingly, we see that there are some households that just have child cases, right, or just have child infections, but you really see this bimodal or multimodal structure in these plots as well, sort of very indicative of transmission, these kind of chessboard plots. And then finally, I did probably most controversially, and this is the thing I'm trying to sort out in peer review, but probably trying to be a bit too careful, is we did a residual. You can do a sort of something in between full regression analysis and that kind of pure exploratory analysis, and look at the residuals, PCR gene patterns. And you could say, supposing for all the pairs of people in households, their strain type or pattern of PCR positivity, which we think correlates with strain type for these time periods, that generally speaking S negatives were alpha variant and S positives weren't. We could look at a null hypothesis in which strains were independent in the household and compare that to one where they're correlated, and we'd expect strain types to be correlated due to transmission. And we do indeed see that, and you see in this kind of residual plot the emergence of alpha as the dominant strain, right? And we also see that the other positives don't cluster with each other, suggesting that they're not associated with this, they're associated with these lower viral loads, right? So this is where we're starting to, so I'm going to show you a DAG later, right? And talk about why this gets complicated, but this is just this final size type approach. So this is, instead of trying to impute everything, we do maths to do the integrals, right? So you can do the integrals in Monte Carlo, or you can try to actually do the integrals over all the things that could have happened. So this is, like I say, Frank Ball's kind of insight is the Selke construction is something where instead of infecting at a rate in like a Gillespie type framework, everyone picks before the simulation an exponential one random variable, and then that's depleted deterministically. And then this manipulation here kind of shows you why that's the same as the normal definition of a stochastic process as kind of a something that happens in an infinitesimal rate. Let's see, looking at time, I won't try, I mean, so, okay, so look, I think I've put all the equations up, but I think I'm just going to have to hope that I can wave my hands at them and people are not going to be too upset, but at least feel that there's some thought gone into this. So what I'm going to use is the multi-type equation, and I'll assume that I can map between all of the different 0, 1s that could happen in a household for outcomes and the integers, so this map iota. And so I can form a vector of probabilities of every possible outcome in the household. And it turns out that that vector of probabilities is the solution to a set of linear equations. So there's just one linear solve per household at a given parameter value. And then you get this rather complex, well, you know, it's not ridiculously complex, but you get this equation for what the matrix B should be. And it takes a lower triangular form, so the solve is quite quick. And there's two components to this. So one is external infection. So the probability that you avoid that is e to the minus lambda, there's a rate lambda. And then what I'm going to do is assume there's a baseline lambda, and I'm going to use a log link function onto a linear predictor, vector alpha dot the feature vector, so that alpha dot feature vector sits in the reals, right, and optimizes like that. And it's also how statistics tends to proceed. But the thing we can interpret is x of alpha, which is a kind of called relative external exposure, right? Okay, so then you can think about, like I said, this is how you can move between a probability of exposure and a rate and a linear predictor, right? And this function here is actually, everyone's probably come across logistic regression, but there's no particular reason to use the logistic as a sigmoid. This is called a complementary log-log, and is used in statistical modeling actually quite a lot. There's a really nice JRSS paper talking about it, and the links with and the links it has with survival modeling from I can't remember who now, but it's a nice paper if I can dig it up if people are interested. Okay, so then there's the within household infection, and this happens at a rate lambda ik between individuals I and k. So the first thing we need to know is the Laplace transformation of the, so the point about household final size is it's insensitive to the mean of your infectiousness. So Lorenzo showed these beta curves, right? It's insensitive to the mean, but it's actually rather sensitive to the shape of those, right? And so you need to know the Laplace transform of the distribution of areas under those beta curves that Lorenzo showed, right? And they can be different for each individual as well, right? So these could pick up a little index I or k, but they're not going to do that here. So in this case, I'm going to assume that everything's gamma just because it ends up with a nice functional form here. And to see why it ends up being a Laplace transform, you look at this Selke construction, and because you've assumed that this this thing here is exponential 1, then you pick up an exponential, which is how you define a Laplace transform, right? So there's no it just follows through actually from this kind of almost elementary manipulation. And in the same way that I kind of tried to transfer onto the reals, I'm going to do that here, so that our predictors sit in natural space and we can do things. Now there's a Cauchy adjustment for household final size, which is used quite a lot in literature, and Frank Ball and Lawrence Shaw did some nice work systematically looking at this versus having an effect for each household size. And basically in this framework, it turns out that Cauchy adjustment is equivalent to taking log household size in the linear predictor. So I think it'd be nice to investigate that in future, but I think the Cauchy adjustment is a pretty standard way of dealing with household size. Okay, so what do we do? Write down a likelihood, that the likelihood is a product of probabilities from the linear solve, fitting that to 3 million observations on a Windows server that you have to log into is non-trivial and means that you need to code things carefully. Here I eked it out with NumPy, but in future, this has now been ported into Number, which is sort of fast, simple linear algebra for Python. Again, there was no chance of doing MCMC, so to do a Bayesian approach, it really helps to have a bit of prior, right? Because the likelihood surface is so complex. Ideally, like I say, that would have been MCMC, but given that it was hard enough just to optimize, do a Laplace approximation, which is, better than nothing, and to ensure we hit an optimum, did multi-restart numerical optimization. I don't think the Laplace is too bad, actually, because you just want an idea of how uncertain you are. And if you look at the point estimates and credible intervals that we get, they're actually pretty reasonable, that there's no... so these are hard to interpret. What I'll do is I'll say the overall infection from outside was very low in tranche 1, which was our kind of summer lull. Then there were 3 periods over wave 2 or 2.5, where the overall probability of getting infected was quite high. Within household infection, pretty constant, although arguably lower in the first wave. So there's this interest in did the transmission parameters change with seasonality or behavior or whatever, but then I would say pretty consistent across waves. The baseline ones this is. And then interestingly, the effect sizes, so the most interesting one here is that what I've written here is CT other, but as I guess gene positivity. Having any type of failure apart from S gene failure is associated with much lower transmissibility, as you'd expect, because it tends to be lower viral loads. Having an S negative, so an S gene target failure before the emergence of alpha is associated with being less infectious. After the emergence of alpha is associated with being more infectious. So this is the strongest thing. Then I think slightly, maybe not underpowered, but maybe the model is maybe the model needs a bit of tweaking to pull out the effect sizes for children. So, you do see one of these coming out as significant, like, the high school children here being less susceptible. Overall, I think this might be slightly over-regularizing the problem with the prior, or despite the huge data set size, a lot of these things are quite collinear, so maybe needing a bigger model. But we do see working in patient-facing is extremely risky. Then we see the schools being open is risky, but for younger children, the schools being open wasn't risky until we got alpha, basically. And some people do think that alpha preferentially made risks sort of higher for younger children. And then when the schools shut, the relative external risk goes down again, which is not the result anyone wanted, because we would like to keep schools open. But you just have to say what the science is telling you, I think. So just quickly then on some other stuff that we've done in the ONS study. If you, this directed acyclic graph here is just showing how, all the things we think are going on, right? So how infectious you are is probably related. So CT is kind of at the middle of everything here, but we think your CT count's related to that, which tells you something about virus. And, that there's probably even more than this, but like, if you really think about what we know, there's solid evidence is going to influence what it's everything, right? So this was a study that's out in eLife looking at CT values. So sorry, for people who don't know, the CT value is generally higher for lower viral load and lower for higher viral load. So it's an odd, it's just a pain really, basically. And what we do is we see that the high CT is associated with full gene positivity and being symptomatic, or being an alpha during the region when at the time when alpha was and S negative and so on. And that it changed over time. So there's also a time, so in that bag, there should also be time, that was at the individual level, but time is a big effect whether the epidemic's rising or lower and changes your viral load. So think about generation times, but of course that is your rate of transmitting. that probably changes over time at the population level, you know, if we think CT is right. And then the other thing about that is this sort of study is really a prevalence study. We're not seeing the new infection. Well, you see a new infection when someone was negative, then you follow them up again, then they were positive, but you don't see it happening in such a direct way as in test and trace type data. So there's a nice, talking about the PLOS magazine link, there's this article in PLOS about how incidence and prevalence get related. So this is a discrete convolution. So work with the Cambridge Biostats unit, we kind of developed the method for checking for consistency between duration of positivity as observed in the data and during the times where we had the full 1 week follow-ups, and so that duration can be convoluted with incidence to make a prevalence. Then you can numerically deconvolve prevalence and check that everything is reasonably consistent, which it is, despite Robert Peston's rather unhelpful intervention, where he set everyone, he got everyone in the ONS very upset by saying that they'd given the wrong data going into lockdown 2, but it turned out it was right. So that is explained here, and in a notebook I presented. So if people want to ask about why we should take Peston maybe less credibly now that he's kicking off about reinfections and other things, then do let me know, despite his excellent economic coverage in the past. So there we go. So I'm showing figures here, but just saying the reason there isn't one is that transmission, does transmission happen at all, is hard enough. How there's a kind of overall population level change in viral load is quite hard, and how incidence and prevalence relate to each other is quite hard. And you've seen hopefully people have seen the maths from other people who've saved me having to do that, of why all these things relate up to give you a generation time. But it would be nice to do a temporal analysis of the household data we've got. So it's on the cards, but we're kind of, you know, blasting through trying to solve these other problems first. So thanks to the ONS team, who are brilliant, colleagues at Manchester, Juniper, people who fund us. Yeah, lots and lots of people fed into this thinking. So I've actually finished quite early, having thought I had a bit too much. So I could always go back and do the maths in excruciating detail, but I think I'd probably better to wait for questions. So thanks, everyone.
Thanks very much for that. Another really interesting talk. So yeah, we have plenty of time for questions if people want to put some in the Q&A. I'll just ask one while hopefully people are lining up some questions, if that's okay. I was just curious about the, so you mentioned that with the Alpha variant, that opening the schools made a big difference. And I was just wondering if you had a feeling with the Delta variant at this point.
I think it's more of the same, actually, that when you say something's preferential in children, of course, it's from quite a low baseline. Mm-hmm. And those credible regions are very wide, so can probably be reduced. And I suspect that the, you know, if you think children have a lower viral load to begin with, anything that increases the viral load is probably a bit nonlinear, so probably does increase the relative risk of children a bit. I think that's the intuition, but it's not. I don't think these are numbers to panic about, because actually the thing I didn't show and probably could have done is when you look at these relative risks of children, if you divide them by the number of extra contacts that children have when the schools are open. Yeah, so this is looking at within household transmission. I think actually what the relative risk externally shows, although it goes up when the schools are open, nothing else was open then. That was lockdown 2 and 3. It was quite a severe lockdown, and at the time the ONS asked those children what their numbers of contacts were, and that number of contacts divided by the relative risk was much bigger than it should have been, right? They had so per contact in school their risk was very low. And so I think that although we often think within household contacts is the typical way we measure generation time, they are more intense, and particularly more intense between parents and the children they care for, right? And I think that parents and children they care for in a household are not as likely to be careful when one of them is symptomatic, or certainly when the child is symptomatic, right? Than you would be if you were out in if a child was asymptomatic at school, they probably still play, right? So I think you have to be very careful interpreting these data, and lots of people jump on them depending on, schools is obviously very emotional, right? It's a very emotive issue, and people will jump on this, but I think it's like everything, it's a mixed picture where schools unfortunately play this intermediate role. They're not nothing, but the risks are very, very clearly much lower relative to adults, and particularly when you compare to flu and other endemic respiratory disease. It's a really odd pattern with age, and so it's just a complex one.
Sure, yeah, thanks for that. Right, we just had one question come in. So is there any way to use this data in a dynamic way to develop a real-time assessment to take public health decisions?
Yeah, so it goes in, I mean, the ONS study, so I don't know if the anonymous attendees from this study has, like, they produce 3 reports a week for government and publish every Friday and all sorts of stuff. And the UK Office for National Statistics is kind of, I didn't know that much about it before this, except that it does the census and various other things. But from working with them, I mean, they're under this tremendous pressure from the statistics regulator, and they're not tremendous. I mean, they're pretty well resourced, but they are expected to get everything right instantly, and work fantastically hard on that. So they're much more careful than we normally are as academics, and I think that's good, actually. So they try to get stuff done quickly, and are a bit methodologically conservative, as in if you propose to use a new method like this convolution one, it has to go through a set of checks if it's going to have the ONS badge on it. And like I say, that's why they're sort of thrust into panic if someone like Peston says they've got something wrong. But I think it's in terms of influencing policy, that gives them a tremendous weight with government, that they work so hard at these things. And if there's they will prioritize and resource analyses where there's a good reason to do them to influence a decision, all sorts of times. So I think that's very impressive. And I think a lot of us, I don't know if one of them's an attendee, but I bumped into someone working there who I'd been the external PhD examiner for. I think lots of our undergraduate and postgraduate students probably end up working for ONS, using the skills we've trained them in, without very much personal recognition. So yeah, sorry, I know that was a very quick question, but it's saying this is all part of an enormous effort to produce these three or four reports a week, and they are used very directly by government and NHS and other stakeholders.
Great, well, thanks very much for that. I think if there are no other questions, we might try and finish the session 10 minutes early. We're just trying to contact the speakers of the next session, so hopefully we can start 10 minutes early. So we were due to start again at 12 o'clock, I think. So maybe we could try and